Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see we have a bunch of questions either saved up from last week or submitted on our form. I also gather that there's now a bot that's announcing these live streams on Twitter. So pay attention to the bot, like as opposed to, I'm thinking of Wizard of Oz, but that's not very relevant. In any case, let's see questions here. Okay, there's one from Peaceful here asking, can I explain why Earth's air doesn't escape into the vacuum of space, considering that gas expands to fill the available volume if it doesn't have a container? Okay, that's a interesting question. It's should be, famous last words, so should be a fairly easy piece of physics to explain. So in a gas, there are molecules that are going around in random directions, and molecules in typical air, molecules collide. The distance between collisions is actually very short. These molecules are always colliding, they're always going in random directions. And if you don't have any container around the gas, these molecules will eventually, they'll go into some random direction where they've never been before, they'll expand out, and that will make the gas expand out. So the molecules will end up going in the random direction to if you don't have a container there, well, what do you have instead? Maybe you have a vacuum where there are no molecules at all, and that means whenever a molecule gets to the edge of the place where there are lots of other molecules, it'll just keep going because it isn't colliding with anything, and it'll expand outwards into that vacuum. So the question is, and that's what generically happens with a gas. And the pressure of the gas is the amount of when a gas has a pressure, that means it's pressing on some container that it has. And the pressure is the force divided by the area. So it's the pressure is determined by the number of molecules that hit the edge of the container. Every time when a molecule hits the edge of the container, it bounces off. It's kind of like a mirror. It's like a billiard ball hitting the side of a billiard table. It's the molecule hits the container, depends on exactly what the container is made of, exactly how the bounce happens, but then basically it bounces off. When it bounces off, its momentum is going in the direction towards the edge of the container, because otherwise it wouldn't be going in that direction. Then that momentum is turned around, it's going back the other way. And when that momentum as it's turned around, the molecule is pushing the edge of the container out to conserve momentum, because that's Newton's third law. It's every action there's an equal and opposite reaction, or in other words, things it's like if you're there are lots of different effects that all come down to the same thing, where momentum that is the momentum of the molecule is reversed, and so that momentum is transferred to the walls of the container. And so that's what leads to the pressure of the gas, is molecules hitting the wall and bouncing off. And the pressure is proportional to, well, basically two things: the number of molecules per unit of volume and the speed of the molecules. And also, I guess the mass of the molecules enters in some way also. But the speed of the molecules, for example, is proportional to the temperature. Temperature is determined by the average energy of the molecules, and kinetic energy is a half mv squared, where v is the velocity, m is the mass. And so that means that the temperature and the pressure are related. Okay, so why does the gas not escape from the Earth? Well, the answer is those molecules that are going out, that are trying to escape from, let's say we think of the atmosphere of the Earth as just a giant box of gas, and there is no, on the surface of the Earth, there's a solid surface, and when the molecules hit it, they bounce off. But when the molecules are going out towards space, there's no boundary there. So you would think the molecules would just keep going, but they don't. Why not? They don't because of gravity, because molecules have a mass, and like anything else with a mass, they get affected by gravity. And so a molecule is going out, it's trying to make it outside the Earth's atmosphere, and eventually it will just get turned around by gravitational force, and it will get pulled back towards the Earth again. And so the real question is the speed of the molecule in the gas larger than or smaller than the escape velocity of the Earth? So if you just shoot a rocket up from the Earth's surface, if the rocket isn't going very fast, the Earth's gravity will just pull the rocket back down again. There's a critical speed at which, if the rocket is going that fast, it can escape the gravity of the Earth. That critical speed for the Earth is 25,000 miles an hour. And so if you shoot a rocket and it gets above 25,000 miles an hour, it can escape the gravity of the Earth, and it can go as far away as it wants. If it's less than that, eventually the rocket will get pulled back down by the Earth's gravity. And so it's the exact same thing with molecules. So in fact, the molecules so then you have to ask, well, how fast do the molecules in a gas go? And as I was kind of explaining, the speed that the molecules go at is related to their energy, and their energy is related to their temperature. And so as soon as you have molecules in this gas not going, for example, in gas at room temperature, the molecules are basically going in air, are more or less going at the speed of sound. That's not terribly surprising, because sound is compression waves in the air. And we know that the maximum speed that you can get a compression wave to move in the air is the speed of sound, but that's also the speed that the molecules are going at. And if you wanted to send some signal through the air as represented by the pressure of the air, the compression of the air, clearly it's not going to be possible ordinarily to have that travel faster than the speed at which the molecules are actually moving and bouncing around in the air. So the speed of sound is related, there's actually a factor of √2, if I remember correctly, between the speed of sound and the speed of the molecules in the air. So that the speed of sound is about 650 miles per hour, I think, at standard, at sea level and so on, at standard temperature and pressure. So that's much less than the escape velocity. So molecules if you took molecules from sort of from this room, for example, and you tried to get them to escape from the Earth's gravity, they wouldn't escape from the Earth's gravity. Now, okay, so there's a tricky point, which is that let's see, how does this work? See, this is always the problem. These questions where I think this is really simple, I realize, wait a minute, I have to explain, I have to think through something, and it's not quite as simple as I expected. But one feature of the Earth's atmosphere is that the most common gases in Earth's atmosphere are nitrogen and oxygen. But in the universe as a whole, by far the most common element is hydrogen, followed by helium. And so the question is, why isn't there hydrogen and helium in the Earth's atmosphere? In the atmosphere of Jupiter, it's mostly hydrogen. And so why is it that Jupiter manages to keep hydrogen in its atmosphere and Earth does not? The answer is the escape velocity of Jupiter is much higher than the escape velocity of Earth. And what happens is and this is where it gets a little tricky, and I have to think through how this works and how to explain it. But essentially the point is that a hydrogen atom a hydrogen molecule on the Earth can, at a certain temperature, will be going fast enough that it achieves escape velocity for the Earth, so it escapes from the Earth. So probably the very early Earth did have hydrogen in its atmosphere, but after a short time, every time there's a hydrogen atom that's sort of going out towards space, it's going fast enough that it can escape the gravity of the Earth, and it just dissipates into space. But for an oxygen atom, it doesn't succeed in doing that. And the essential reason for that is that what matters to escaping from a gravitational field is the escape velocity, but what matters, the temperature is determined by the kinetic energy, and that's a weird thing. Kinetic energy is proportional to mass times velocity squared. And so that means that if the mass is, for a given kinetic energy, if the mass is lower, the velocity will be higher. And so that's why if the mass is lower, like it is for hydrogen as compared to oxygen, the mass of a hydrogen atom is basically 1 atomic mass unit, whereas the mass of oxygen is 16 atomic, yeah, that's right, 16 atomic mass units. So oxygen is 16 times the mass of hydrogen. So that means that its velocity at a given temperature will be, with the square and all that kind of thing, it will be a quarter the velocity of the hydrogen atom. And that difference is the difference between managing to escape from the Earth's gravity, but not escape from Jupiter's gravity for a hydrogen atom, for a hydrogen molecule. I'm cheating a little bit here because the hydrogen molecule, which is H2, and just a few bits and pieces of formulas and things, but that's the basic idea. The basic reason that the atmosphere of the Earth does not escape is because it's held to the Earth by gravity, but some gases don't end up with their molecules going faster, and so those do escape, and that's why you have different constitutions for the atmospheres of different of planets of different sizes. So let's see, there's a question here that sort of relates to what we were just talking about from William, asking, why are there phases of matter? Are the phases real, or do they depend on what we can observe? Okay, that's an interesting question, which starts elementary and then has a big hook to something quite non-elementary. All right, let's talk about the basic question of phases of matter. So, one knows for water or something, there are basically 3 forms in which water can come: ice, solid, liquid water, and gas, steam. And what is the difference between those phases? Well, we kind of know intuitively what the difference is. In a solid, it all moves as one block, and it's kind of hard to deform. And if we look microscopically, all the atoms or molecules will be kind of arranged in a fixed array. In a gas, on the other hand, at the opposite extreme, the molecules are all separate and they're all just bouncing around and they're randomly colliding with each other. Liquid is an intermediate case where the thing can kind of, if you try and sort of squash a liquid, it's typically very hard to squash. If you try and shear a liquid, it typically has a resistance to being sheared, significant resistance to being sheared, but nevertheless, it can flow in a way that is where the liquid, pieces of liquid can go sort of anywhere, so to speak. They're not all in one block. Okay, so why do things work this way? Why are there, for example, 3 phases like that? Actually, it's more complicated than that, because there aren't, for solids, for example, there can be many phases. So, for example, in cases where there's several different kinds of solids. The most common kind are crystals, where the atoms are all arranged in a very regular array. So, for example, a salt, table salt, sodium chloride, is a crystal, and you may notice if you look at the little pieces of salt that they're cubes. And the reason they're cubes, they're usually cubes at least, the reason they're cubes is because inside that salt crystal, there are lots of sodium and chlorines, and they're arranged in this regular cubic array. So if you look down at sort of a microscopic level, you would see something which is kind of like lots of lines of atoms that form this kind of cubic array. So, for example, if you look at something like a diamond, for instance, well, it's often a bit confusing because diamonds are cut in special ways. But if you looked at a raw diamond, you would find it has a certain, and you looked at the carbon atoms that are inside it, you would find they're arranged in a particular kind of array that doesn't happen to be quite the same as the sodium chloride cubic array. But different kinds of, there are actually 26 kinds of crystal arrangements that you can have, 26 so-called Bravais lattices, and they're the different kinds of ways that you can arrange atoms and molecules so that they have the feature that there's one block and then another repetition of that block and then another repetition and so on all the way through the crystal. So what is happening there? Well, what's happening is when, let's see how to explain this. The fundamental thing that's happening between these different phases is in a solid, the atoms or molecules are kind of more or less just sitting there next to each other in some kind of arrangement, and they might be wiggling around a little bit as a result of temperature. Temperature is what temperature is microscopically is the energy of individual molecules. So temperature, the formula is the energy per sort of degree of freedom, per sort of direction the molecules can move is half a thing called Boltzmann constant K times T, the temperature. That's the average kinetic energy of your random atom at a temperature T ends up being 3/2 kT. So the thing that so temperature is proportional to the average energy, measures the average energy of a molecule. One tricky thing, when you say temperature measures that, when we measure temperature, like we say it's about 70 degrees, it's about 20 degrees Celsius here, that word degree is kind of telling us that this is not an absolute scale of temperature. This is temperature relative to some zero of temperature. So for example, degrees Celsius is measured relative to the melting point of water, the 0 degrees Celsius, that's the zero of that scale. But there is an absolute scale of temperature, the so-called Kelvin temperature, and that's something where and when we talk about these formulas where the kinetic energy is proportional to temperature, that temperature scale is the absolute temperature scale. Okay, what does it even mean that there's an absolute temperature scale? All these things are kind of connected. The temperature is measuring the kinetic energy of molecules. It's measuring how quickly molecules are sort of bouncing around. So then that suggests that there has to be an absolute zero of temperature where the molecules aren't bouncing around at all, where there's essentially zero energy in the molecules. And that's correct. That's how it works. And that zero of temperature is about minus 273 degrees Celsius. That's so-called absolute zero, at which, in a first approximation, if you cool things down to that temperature, all the atoms and molecules that would otherwise be bouncing around with a certain kinetic energy, they'll all just be staying still. Now, a little bit of a footnote, they don't quite stay still because of some effects from quantum mechanics, which I can talk about, so-called zero-point energy. But in a first approximation, and sort of the basic physics explanation is when you get down to absolute zero, the atoms or molecules are just staying still. When the atoms or molecules are staying still, they tend to, then they're pretty much guaranteed to be a solid. And the reason is that there are forces that cause molecules, for example, to attract each other. And that means that when you have all these molecules and they have no kinetic energy, they're all pulled together by these small forces that attract the molecules together. And that means they're all pulled into this thing that ends up making itself into this pure solid, usually a crystal. The reason that molecules, there are essentially electrical forces that cause molecules to always have a certain force of attraction between them. And that's what will make them form into something which is a solid. So at absolute zero, almost everything is a perfect solid. Of course, there are always exceptions to things. And helium-4, a certain isotope of helium, is not a solid at absolute zero, at least at ordinary pressure. It's still a liquid there. And the reason it's still liquid is because of quantum mechanics effects. And it's the sort of the weird exception. But most things are solid, even all the gases that we know in, nitrogen, oxygen, hydrogen, they're all solids at absolute zero. Because the molecules in them have this force of attraction between them, and they have no energy to sort of bounce around and escape from that force of attraction. Okay, as you heat things up, there comes a point where those forces that pull molecules together are irrelevant compared to all the energy the molecules have just as a result of temperature, just as a result of heat in the material. What heat is the microscopic motion of molecules. And so as measured by temperature. So when there's enough heat in the material, high enough temperature, that means the molecules are bouncing around, and the fact that there's this tiny force of attraction between them is irrelevant to these molecules. They're just going around as a result of the heat, and then they collide, they bounce off each other, and the fact there's a force of attraction is basically irrelevant. And that's what happens in a gas. And so when you increase the temperature of a material enough, it will turn into a gas. Okay, footnote, if you increase it even more, it will turn into a plasma. If you increase the temperature even more, the electrons inside the atoms will get stripped off the atoms, and the thing will become an electrically charged plasma. But that's what happens in fire, for example. But in ordinary materials, as you increase the temperature, it will turn into a gas. Okay, so as you cool it down, eventually those forces of attraction between atoms and molecules and so on get large enough that it condenses into a liquid. The process of condensing into a liquid is, even after all these years, not very well understood. Liquids are really hard to understand in terms of sort of the mathematics of what's going on in a liquid. But what tends to happen is the gas will get to the point where there are forces that will cause the atoms to kind of stay together, but they can still move around a bit. Okay, then when you cool it down further, the thing will freeze into a solid. And at that point, the forces are strong enough that they will just keep the atoms or molecules kind of locked together. Now, often if you say, well, let's take carbon, for example, in what way can carbon atoms be arranged? Well, one way they can be arranged is a diamond lattice, where there's a particular crystal arrangement that makes diamond. Another way they can be arranged is in graphite, the kind of thing you find in pencils, which is very sheet-like. They're arranged in kind of sheets of atoms. And both of those are perfectly valid solid forms of carbon. They are different phases of carbon. They're different solid phases of carbon. And so many things, most materials that become solids can have many different phases. And usually those phases, when you change the pressure, for example, you'll get a different phase, a different arrangement of atoms, different arrangement of molecules. So for example, water has, I don't know how many phases on, but about 10 phases that are known of solid phases. And most of the time, we don't notice those. But a glacier, for example, which is water at the bottom of a glacier, for example, there's a very high pressure because there's all this force from lots of ice on top pushing down on the ice underneath. And so the phase of you end up with the molecules of water arranging themselves in a different way. And so you get a different phase of ice there. And in fact, phase changes are important. For example, in the rocks that make up the Earth, there are many different phases of the rocks. And sometimes phase changes, I am not completely sure what the latest theory on this is, but it certainly used to be believed that phase changes were important in earthquakes, and that was one of the things that could, as you change the pressure of a rock, you can change the phase that the rock is in. And when you change the phase, when you change the solid phase, as the atoms rearrange themselves, for a given number of atoms, the volume that those atoms can take up may change. And so, for example, you crush the thing hard enough and suddenly the atoms will rearrange and the thing will become smaller. It will have a higher density, it will have a higher mass per unit volume, but it will become smaller when you crush it because of the rearrangement of the atoms, and that can lead to potentially some discontinuous change in the structure of the rock and give you an earthquake or whatever else. But so, okay, so this idea of solid phases, there can be multiple ones. As you heat the thing up, the atoms they jiggle around a little bit, but they stay more or less in their place. And then eventually the thing melts and the molecules start moving around kind of randomly in the water. And then when you heat it up further, the molecules escape the water and the thing becomes a gas. So a question you might ask is there only one liquid phase? Or could there be multiple liquid phases? Well, nobody knows. There have been claims every so often that there are multiple liquid phases, and there are some situations actually with water. Water is a particularly complicated substance. There are claims that there are kind of these within liquid water, that there are these kind of clusters of molecules which behave in a different way from what you would think kind of the overall bulk liquid, where every molecule is moving around any place it wants might be. But it isn't really known whether there can be multiple liquid phases. With gases, sort of inevitably, there can only be one phase because the molecules are sort of bouncing around randomly. There's no kind of arrangement of molecules. Now, the question of are these the only phases, solid, liquid, gas? Are they the only conceivable phases? Well, things are more complicated. So, for example, most of what we're made of is this kind of as a sort of gel type phase, which is something that doesn't normally happen with a single substance. But when you have kind of the cytoplasm of a cell, for example, it's made up of many different kinds of molecules and it's got water in it and so on. And that is a phase where things are kind of squidgy, but they don't flow like water. And they're not sort of solid they're not perfectly solid. Another thing that's weird is glass and glasses. If you in a glass, like a pane of window glass, the molecules don't form a crystal. They're not arranged in a nice regular way like they would be in a diamond or something like that. Instead, the molecules are sort of packed in randomly. That's the defining feature of what's called a glass, is that the molecules in the case of window glass or something, it's silicon dioxide, basically comes from sand, it's a version of that has the molecules just sort of packed in randomly, and that actually means that if you have in a crystal, the thing is sort of rigidly locked down to be sort of arranged in that grid of positions of molecules. In a glass, they're not as rigidly locked down. They're sort of in random positions. And that means that, in fact, the glass can very, very, very slowly flow pretty much like a liquid. So if you see, window panes that were put in, 400 years ago or something, you'll often see that they have thickened at the bottom because very slowly the glass has flowed, because these molecules, they're not locked in place as they would be in a crystal. They slowly can rearrange themselves in that way. So a question you might ask is, could it be the case that there are, and I think this is probably William's question, could it be the case that there are sort of phases of matter that where what we notice about solids, liquids, and gases is, from at the scale we're at, we can pick up something that's solid, we can paddle around in something that's liquid, we can we can inflate a balloon with something that's gaseous, and with those ways of interacting with materials, with the ways we normally interact with materials, it's pretty obvious. The solid, liquid, gas classification is pretty obvious. But let's imagine that we were organisms which are very tiny compared to us, for example, or let's imagine we're an organism that, I don't know, it's a tiny little organism that has these giant filaments that come out from it that sort of sense the environment nearby. And let's imagine we put that in, let's say, water. Well, it could be the case that, for example, this question about the clusters of molecules in water, actually, let's take the more extreme case of a gas. We think there's only ever one phase of gas because all the molecules are kind of bouncing around randomly. But maybe there are situations in which there is microscopic non-randomness in the gas, which a critter that was, size of molecules with all these long tentacles and so on might be able to sense that we just wouldn't notice. We'd say the gas looks random to us. So it certainly is possible that if you're looking for different kinds of things, you would conclude that there were different phases of matter. Let's think about that for a moment. The question would be, can we imagine an imaginary organism that would come to different conclusions about how, here's an example. Okay, so one slightly odd form of matter is liquid crystals. So in a crystal, as I explained, all of the molecules, for example, I keep on sort of alternating between atoms and molecules because in something like sodium chloride, you're not really dealing with a molecule of sodium chloride and another molecule. The sort of individual atoms are kind of separately in there in the crystal lattice. Whereas other things like water, there really is an H2O that's there, and then there's another H2O next to it. So it's sometimes one's really talking about things where there are molecules sort of in that you can identify, and other times it's kind of atoms arranged in a certain way. But in any case, liquid crystals. So in an ordinary crystal, solid crystal, you've got atoms or molecules arranged at these in this lattice, in this regular array. What is a liquid crystal? A liquid crystal is something where it has long molecules in it, and the positions of the molecules are moving around randomly. The molecules are sort of bouncing around randomly, just as they would in any old liquid. But they're long molecules, and so they have an orientation, and that orientation can get lined up. And so, in a certain phase of the liquid crystal, I think it's the smectic phase, I'm trying to remember, is that the right phase or is that the one where anyway, whatever. There's a phase of the liquid crystal where all of the molecules are lined up. So they're moving around randomly, their positions are random, but their orientations are aligned. And for example, when we have liquid crystal displays, the way those work is when you put an electric field across the liquid crystal, then you can arrange for these molecules to all line up. When they're all lined up, they don't let light that is polarized, that has its electric field, for example, sort of wiggling in one direction, they don't let that kind of light through the liquid crystal. So that means that when you put the field on the crystal and all its molecules line up, you're blocking some light from getting through, and so that pixel will look black, for example. But in a liquid crystal, then the idea is you've got this alignment of molecules, but not positional order of the molecules. So I'm sort of imagining a critter that for which the most important thing about it is the alignment of molecules. And then it's going to conclude that, for example, well, actually even a more extreme case. Okay, I got a better case. In a liquid crystal, okay, so in a fluid, you have vortices. So the fluid can flow, it has a certain velocity, it's all going in one direction, but the fluid can also have a rotation, a piece that's a rotation. You can see, when water is draining out of a tub or something, you can see it forming this vortex. Or you can, when you just run your finger through water, you'll see behind your finger there's little vortices that start up where the water is circulating around. The big time version of that is a hurricane in the Earth's atmosphere or a tornado. Those are vortices. And in a vortex, the big feature of a vortex is once the circulation has started up, you can't make the circulation disappear. There's no way to just sort of say, oh, this air or water that's going on in this direction on one side, that direction on the other side, those two things, you can't sort of smoothly get rid of the presence of that vortex. It's a so-called topological defect. And the only way to get rid of it is to sort of damp the whole thing out. So in water, for example, or in air, you can have these vortices. In liquid crystals, you can actually have more elaborate kinds of structures which have the same kind of topological character of sort of, as you go round a circle, you end up with this sort of, in a sense, as you go around a circle with in a hurricane, for example, you can say, well, the air keeps on rotating in the same direction around the circle. And there's a more complicated version of that. This is related to the mathematics of homotopy, and these are so-called homotopy groups that in fancy mathematical terms, it's all about pi1 of S1 is the thing that determines the fact that, yes, you can actually have a hurricane, so to speak, is, you know, the pure math of that has to do with kind of the winding number. Can you tell, okay, so the way this comes from is, imagine you have a piece of string. You can, as you pull on the ends, the thing will eventually get straight. But let's imagine that the piece of string was wound around a pencil. Just once, you pull on the ends, it's still wound around the pencil. Okay, you can't deform that to get to something where it isn't wound around the pencil at all just by pulling on the ends. Let's say you wind it around the pencil twice. It's got a winding number of 2. Pull on the ends, you can't change that. You can't change it to a winding number of 1 or 3 or anything else just by pulling on the ends. You have to unwind the string and rewind it to get it to a different winding number. There's more elaborate versions of that when you're not just winding a one-dimensional thing around a sort of a one-dimensional pencil, but where you're, for example, here's an example of one. This is a famous one, is can you comb the hair on a tennis ball? So the question is, you've got this sort of tennis ball, it's got its sort of furry tennis ball, and you ask the question, is there a systematic way to comb that fur, so to speak, so there'll never be a defect in the fur? So you just smoothly make, you know, the fur's going this way, this way, this way. As you go around the tennis ball, you'll never have a place where there's a discontinuity in the direction of combing of the fur. Turns out that's not possible. And there's always there has to be somewhere on the tennis ball where there's a discontinuity in the kind of combing direction for this hair. And that's a slightly fancier version of the same winding number question. So what I'm imagining is a critter where all it cares about is vortices or generalizations of vortices, and perhaps the more fancy version of that happens in liquid crystals, which is more like the hair on a golf ball, on a tennis ball thing, and a more elaborate case. So the question would then be, is it the case that you could imagine a critter where for it, the most important thing is phases that were associated with vortex numbers and things like this? Yes, you could imagine that. And then its conclusion about the, quotes, phases of matter will be very different. It would say, what really matters to me is whether this water has lots of vortices in it, not whether the water is flowing like water does or is like a gas and so on. So yeah, I think an interesting point. I think that probably is observer dependent what the phases are, and actually it's a good thing to think about. All right, we're on a kind of a bit of a physics kick here. Actually, Parmenides is commenting that sodium chloride makes incredibly square crystals. Yeah, it's really remarkable how, you know, it's an interesting thing about crystals. Okay, you might say, okay, sodium chloride, is always going to make a cubic crystal? For example, ice. The phase of ice, the most common phase of ice, is a hexagonal crystal phase. And one's certainly aware of the fact that there are hexagonal snowflakes that are just hexagon shapes. That's when snow is not very fluffy, then that's usually when it's kind of icy and things. That's when there are pure hexagons that can slide pretty easily really relative to each other. That's what the crystals of ice look like. But we all know that you can also have snowflakes, and they're also ice crystals. And if you looked microscopically at the arrangement of water molecules inside a snowflake, they're all perfectly lined up, just as you would expect in an ice crystal. But the outer boundary of the snowflake is not just a hexagon. So in the case where the outer boundary is a hexagon, it's kind of just reflecting the inner kind of positions of the molecules. It's just as if you have a certain arrangement of molecules and you're stopping at some point, and that outer boundary reflects the inner structure of the molecules. When people first started studying crystal structures about 300 years ago, that was, I mean, people had observed them earlier. That's probably a original kind of motivation for identifying some of the platonic solids, like the well, particularly the dodecahedron, probably, that was seeing that in crystals, things like that in crystals. The question then is, does the outer form, the so-called habit of a crystal, does it reflect the arrangement of atoms inside the crystal or not? Well, the answer is sometimes it does and sometimes it doesn't. So when you have a fluffy snowflake, a snowflake that has lots of arms, where the arm makes arms and it's making kind of a tree-like structure, usually called the dendritic snowflake, a dendritic structure, after the Greek word dendron for a tree. The dendritic crystal, also microscopically, the molecules are arranged the same way, but the outer boundary is not arranged the same way. So why do dendritic crystals form? Why isn't it the case that once you have this inner kind of arrangement of molecules, why doesn't that end up determining the shape of the whole crystal? Again, it's a bit complicated, and people, actually, I've made some contributions to this particular question myself. It turns out the critical effect is the following. You have to ask, how does a new molecule get added to the surface of a crystal? Because when a crystal grows, it's got to be, it's growing a molecule at a time. They're like, for example, I don't know, you can grow crystals out of liquids. You can grow, a copper sulfate crystal or something, and it'll you hang it on a string from a seed crystal or something, and it'll gradually accumulate copper sulfate, and you'll find it has this nice parallelogram type shape that comes out. At least in principle, it does. I remember when I was a kid trying to grow those things, they often didn't work, but that's a different matter. But in any case, what's happening in the growth of one of those crystals is there's the solid surface, a molecule of copper sulfate is hitting that surface and it's getting trapped because there's forces that attract it to the surface. When it gets close to the surface, instead of bouncing off, it just sticks on the surface, and gradually the solid expands. Now, in the case of a snowflake, as it forms, if the snowflake is forming fairly rapidly, what will happen is the molecule will come in, it'll hit the snowflake, it'll attach to the surface of the snowflake. But that process of attachment, as it locks in to that attachment, it will slightly heat the snowflake up right there. And the reason is it had all this kinetic energy that it was using to sort of bounce around. And as it gets locked in place, that energy has to go somewhere. And that energy gets turned into heat that heats up the local area right around the place where the molecule locked in. And so that heat, so-called latent heat of that is released by the thing becoming a solid, at that point, that heat that's released will then make it less likely that the next molecule that comes along will also stick to the surface if it was right close to the first molecule. And so that phenomenon, one can call it growth inhibition. When something has grown in a particular place, it will tend not to grow at the exact same place immediately afterwards. It'll take a little while before things have cooled down to the point around there where it can grow again. And that's basically why dendritic arms form, because what's happening is a little piece of crystal accretes on one side, and then it says, okay, I don't want any crystal right near me because I just heated things up. And so that means that you'll end up with this arm that grows out, and there'll be nothing right next to the arm. It doesn't fill in right next to the arm because as the arm has been growing out, it's heated things up slightly. So that's why dendritic crystals form, more or less. There's a nice cellular automaton model that I made up at one point that for that, other people worked on it also, that represents kind of the basic essence of the phenomenon of this growth inhibition thing that leads to this dendritic structure, and actually does rather well at modeling the actual structure of snowflakes, because snowflakes, they have arms, the arms grow arms, and eventually if you just look at the geometry of the situation, the arms run into each other and you end up getting back to a hexagonal plate. But it's a hexagonal plate, there's a few little holes in it from where kind of arms collided. That leaves certain holes. And if you look at under a microscope in an actual snowflake, you'll see those holes when it's at the stage where it's kind of got the arms all to have collided. So anyway, dendritic crystals are a thing that is kind of it's still the same crystal structure, but the outer boundary of the crystal, the way in which the crystal grows, is by this process, when it's growing more quickly, it will grow these dendritic arms. Do dendritic arms matter? Well, they make snow fluffy. That's nice. They are. It's important for avalanches, whether the snow has gone to a place where most of the snow that's falling is just plates that are very slippery, or whether it's dendritic pieces of snow that are not so slippery. Another place where dendritic structure matters a lot is in batteries. It's the thing that actually limits much of the energy storage in batteries, has to do with the formation of dendritic pieces inside the material of the battery. And that will then eventually, I guess, short out the battery as these dendritic pieces kind of eventually reach out into different parts of the battery. So anyway, so different crystals can have these different, they can have dendritic growth, or they can have what's called epitaxial growth, which is this growth just in layers in that way. Now, even when they're growing in layers, things are complicated because, for example, I mentioned vortices. When the atoms get attached to the surface, you can end up with these things called screw dislocations, where essentially these progressive atoms that are added aren't quite lining up perfectly. They start being off a bit, and you can't get rid of that off a bit kind of screw-shaped thing, and you form this kind of vortex-like structure on the solid surface. And so that prevents you from having a perfect crystal. You end up with a crystal with these defects in it. And so, for example, when people want to make silicon crystals to make microprocessors, it's a big deal whether the crystal structure is perfect, because to make a chip with 1 billion transistors on it, every transistor is very tiny. It's only a modest number of atoms across the transistor. And if the crystal structure around those atoms is off a bit, the transistor won't work. So it's really a big deal to try and figure out how you make a perfect silicon crystal. And the whole there's a whole art of how you make good crystals and how slowly you let them cool down and all this kind of thing as they turn into solids. There's a lot of different ways to do that. And it's more, I think, an art than a science. It's not really completely known. They're just procedures that people have found that grow really good crystals. But that's an example of where that shows up. Alistair is commenting that this whole dendritic growth thing is how vegetation grows and so on as well. Actually, a little bit different reasons. The main reason plants grow dendritically in sort of tree-like shapes is because plants have rigid cell walls. They have cellulose in their cells. And that means if you're a plant and you're growing, you can't just sort of you can't have something where you grow a little piece and then that puts pressure on the piece that grew before, and you just sort of squidge into a certain shape. A plant is a rigid thing. And so if you want to grow outwards, and for example, you want to expose your leaves or something like this, the only choice in a sense is to grow in this progressive branching type way. And the mechanics of how that works, I mean, plants, they tend to have these apical meristems, they're called, these places where you actually have there's a growing piece to the plant where it's going to add more material, and it can't change what's there already. Once the cellulose cell wall is of the plant, which is rigid for sort of crystal-like reasons, gets laid down, the only choice the plant has is to add another rigid piece. We animals discovered something else. We discovered kind of how to be squidgy, and when a piece of us grows, apart from bones, which also tend to grow just at the ends, when pieces of us grow, you can have like a thing that where you're getting dividing cells and things are growing outwards, and you just, because we're kind of squidgy, you can just put pressure on the other cells and they'll move and deform and so on, rather than you having to have, it's a solid thing and it's got to grow by adding more stuff to this kind of solid structure. The question here from William again: how perfect are crystals? Can they be used to detect microscopic structure of space? Oh, interesting. Crystals, you can get very good crystals. You can get a crystal like a silicon crystal where it is an absolutely perfect crystal, where like a thing, an inch square piece of silicon is perfect. Not a single atom is out of place. Now, is there a way to use that to detect in our model of physics? In the end, space is, people often think of space as just like it's a coordinate. You just say where to put things anywhere in space. We believe, rather increasingly good evidence, that space ultimately is made up of sort of these abstract things we call atoms of space that are just connected in a giant network. And that's what kind of that is the stuff that our universe is made of. And that means that at the lowest level, at a sufficiently small scale, space is just discrete things. And so in the end, you won't be able to make a perfect crystal, because things have to sit at the positions of atoms of space. But the atoms of space don't have a built-in notion of position. The whole idea of position is just determined by these relations, these network connections between these atoms of space. And so there is certainly a sense in which you can't have the kind of perfect with respect to position crystal. But I think the issue is that we don't know what the scale is of kind of the effective distance between atoms of space, but it's probably a trillion, 10 to the minus 100 meters, roughly, let's say. And the actual distance between atoms is 1/10 billionth of a meter, for example, incredibly much bigger than the distance between the atoms of space. The atoms in a silicon crystal might be, some fraction of a billionth of a meter apart, but that's huge compared to the trillionth of a meter that the atoms of space are apart. But it is an interesting question whether you can have enough atoms in a crystal that their collective effects could allow you to detect sort of deviations in the structure of space. And that's an interesting question, and I have not thought adequately about it. And good one to think about. Thank you. Let's see. There's a question from memes here. If atoms of space act like a superfluid, would that mean there are vortices that arise if the universe is rotating? Oh boy. There are definitely the analog of vortices, which can arise in the kind of underlying structure of this kind of giant network that represents the structure of space. There absolutely can be things like vortices. In fact, particles like electrons may very well be the analog, not quite as direct as just things circulating around like a vortex, but the basic analog of a vortex in the structure of this network. I'll give you a bit of an analogy. We don't know exactly how this works, but if you have a network, just a bunch of points connected together to make a graph in the mathematical sense, you've just got all these points, and let's say you connect them with pieces of string, and then you say, can I lay out this whole sort of tangled thing with places where the pieces of string are connected together? Can I lay that out so that it is planar, so that there are no pieces of string ever cross over, that they don't ever have to cross over? You might have one arrangement where there are lots of pieces of string crossing over, but the question is there a way with the connectivity of the pieces of string to lay it out so that the thing is planar, so there are no pieces of string crossing over? So that's a mathematical question, the planarity of a graph. And there's a theorem in graph theory that says there's a condition, there's a very definite condition you can state for whether you'll ever be able to set up the pieces of string so that they're purely planar. And the condition is that certain subgraphs, certain particular local arrangements of pieces of string, there have to be two kinds of subgraphs that are missing. They're called K5 and K33. They're just particular arrangements of sort of pieces of string, arrangements of the graph, and if neither of those local arrangements is present, then you can lay things out in just a nice planar way. But if you have one of those sort of non-planarities present, you can't get rid of it. If you rearrange the string and you even change the structure of the graph, but always preserving planarity, you can't get rid of that thing. And that's kind of like the fact that you can't get rid of that, the piece of string that was wound around the pencil or the vortex in the fluid, same kind of idea. And it's that kind of local stability that we think is associated with the existence of things like electrons, which are essentially in our models of the universe, sort of local regions of space. There's a strange analogy, which we don't understand very well yet. There's a strange analogy between black holes and particles like electrons. It's probably more than an analogy. They're probably really very, very similar kinds of things. A black hole is a region of space where the structure of space is such that, for example, there are things can get into that region but cannot get out of that region. It has an event horizon, for example. It's sort of a place where the structure of space has become very kind of very condensed, and there's this kind of outer boundary which hides everything inside that region. Well, the suspicion is that electrons are very similar to really tiny black holes, and that they too can potentially have, they have a structure just like black holes from the outside. All you can see is, oh, that's a black hole of a certain mass that's spinning at a certain rate. The fact that, oh, it was a collapsed star inside and it had a whole civilization and they were, they've got all kinds of things going on in there, doesn't matter. You can't see that from outside a black hole. And so similarly for an electron, one of the things that's always surprising about electrons is that it seems like every electron in the universe is the same. They all have, it's not the case that it's electron number one, electron number two, and they're all a bit different. Well, that can happen if sort of inside the electron, there can be all kinds of things going on, but it has kind of an outer boundary that prevents one from noticing what's going on inside. And that would be the direct analog of a black hole, although at a very different scale. And that's kind of the suspicion about how that works. And the suspicion is that both of those things, we know for black holes this is the case, but they're kind of versions of kind of like a vortex in space-time. It's not actually a vortex, it's a different topological structure, but it's the same kind of idea. So let's see. The questions. Oh gosh. All kinds of interesting questions here. Calais is noting that diffusion doesn't work in space. And well, okay, diffusion is the process whereby, well, at least diffusion in a gas is something where, let's say you've got a different kind of molecule. Let's say you've got a molecule that we could smell as some kind of, wonderful aroma or something. Well, the question is, how does that molecule, that is the smelling molecule, so to speak, how does it move in the air? And the answer is it diffuses in the air, typically. And what is diffusion? Diffusion is, well, that molecule is here, it hits another molecule, it bounces off, it goes in a different direction, it bounces off another molecule, it slowly moves across the room. And actually what tends to happen is that the distance it will go is roughly proportional to the square root of the time that it's been going for. And it gradually, and that process of diffusion happens, and it happens at that rate because the molecule keeps on hitting other molecules and the molecule is sort of randomly made to go in a different direction. The molecule essentially executes a random walk through the air, through the gas, and that's sort of the rate at which it goes. Now in space, there isn't diffusion because there's nothing for it to hit. There's nothing that will make it walk randomly. Instead, once you have an atom going in a certain direction, it's just going to keep going in that direction, except insofar as it's affected by gravitational fields, magnetic fields, electric fields, these things that are, but it's not going to be like diffusion in a gas, where what's happening is determined by kind of the molecule bouncing around. So that's some, yeah. So the forces that between molecules. So there are different kinds of forces. In, for example, sodium chloride, there are ionic forces. An individual atom with its electrons stripped off has an electric charge and it will attract another individual atom and so on. The forces between ordinary molecules, just like a complete molecule, are so-called van der Waals forces. And those arise in the following way. So when you have magnets, let's say you have two magnets. And those two magnets will have a force of attraction between them. The north pole of one magnet will line up with the south pole of the other, and the magnets will be attracted to each other. And that force is a magnetic force, and that's just a force that exists. We can talk about. If we say, why does it exist? You're going to sort of drag me into talking about our fundamental theory of physics, because the why. In traditional physics, it's just like that is a thing. There are these properties of electromagnetism, and that's just the way it works. Now, for a molecule, okay, so an electric charge, like an electron, for example, has an electric charge. Electric charges, like two electrons with the same charge, they repel each other. Opposite charges attract each other. That's different from the way it works with gravity. With gravity, masses always attract. If there was a negative mass thing, which we don't know exists, but then it would repel. But in gravity, like charges, like masses attract. Whereas in electromagnetism, like charges repel, unlike charges attract. That's in the underlying physics. It's not really an explanation, but the graviton is a spin 2 particle and mediates gravity, and the photon is a spin 1 particle, and that's a way of describing the same phenomenon of like charges repel, unlike charges attract, etc. So in any case, that's how, if you have charged things, there's an electric force between them. If you have, the trickier case is if you have two charges right next to each other, a positive charge and a negative charge, they'll be attracting each other. Then the question is, what happens to another positive and negative charge that's somewhere nearby? That combination of the positive and negative charge is called an electric dipole. It's a two-poled, it's got a plus and a minus in it. It's a dipole. And what happens is that electric dipoles attract each other. And that's more or less for the same reason that magnets attract each other, although it's now an electric force rather than a magnetic force. It's basically the minus part of one dipole is attracted to the plus part of the other, and vice versa. And so they attract each other. Just for the mathy, for electric charges, there's an inverse square law, 1 over r squared. For the force, for dipoles is 1 over r cubed. So okay, so what does that have to do with molecules? Well, it turns out some molecules just have a dipole moment. It's as if they've separated the charges, and they are overall their charge is 0, but they have plus and minus charges separated. Actually, water molecules work that way. Water molecules, that's one of the reasons why water has weird properties, is because it has that dipole effect. But the other thing that happens is that just a neutral atom somewhere, even though it doesn't intrinsically have any of this dipole thing going on, what will happen, oh boy, this actually has a little bit of complexity in it. What happens is, because of quantum effects, there is continual little bit of fluctuation well, the charge is more or less equally distributed, but there's a little fluctuation that causes the plus to go that way and the minus to go that way just for a moment. And then there's another fluctuation that causes it to go the other way and so on. What happens is those fluctuations, when they occur, fluctuations occurring in one atom will induce fluctuations in another atom, and it will induce a dipole moment, which actually is such that these two atoms will attract. So as a result of quantum fluctuations, there is this small sort of dipole to dipole interaction between atoms that leads to this attractive force that leads to even things like liquid helium and so on having attractive forces between them. There's more to say about that, but that's a rough version of that. Okay, there is a question here from Brian. Could photons be frozen at absolute zero? Okay, so this whole story of temperature applies to material objects. It applies, temperature is a story of atoms and molecules running around. Light is made of photons, and the same story doesn't specifically, well, okay, this is a bit tricky. Okay, so normally temperature applies to just sort of molecules in a gas running around, etc. Now, actually, and I realize I worked on this myself in the late 1970s, in the early universe, there are all kinds of other, there were all kinds of other particles that existed, and you can define a notion of temperature for those too. And you can say, oh, there are electrons going around, there are protons, separate protons, there are quarks, there are this, there are that. All these different kinds of things were there, and there's a temperature defined by the energy of all these particles going around. By the way, people asked about phases of matter and so on. In the case of the early universe, there will be a phase at which there are individual quarks and gluons running around, and then as you cool it down, there's a phase at which it's usually called the quark-gluon plasma, and there's a phase, as you cool it down, particles like protons and so on start forming. You kind of get these droplets formed out of this plasma of quarks and gluons, which otherwise is just this thing that's sort of like a gas or liquid or something, where these things are just sort of flowing all over the place. And then the nature of that particular kind of system is such that it always forms at lower temperatures. It makes droplets, and those droplets are the particles we have, like protons and neutrons and so on. But in any case, so there is a notion of temperature for other particles like quarks and so on. There isn't really a notion of temperature for photons, because photons always go at the speed of light. And this idea, let's think about this for a second. I mean, photons have an energy. Their speed is always the speed of light, but their energy is determined by the frequency of you can think about it as determined by frequency of the color of different colors of light have different energies of photons associated with them. Now, the question would be, what is the analog? Well, okay, so so what's the analog of a different phase of light? The answer is a laser. A laser is the analog of the solid phase of light. And so what happens in a laser, ordinarily in light, you have a incandescent bulb or something, if anybody even has those anymore, or an LED light. Well, the incandescent bulb is an easier case to explain. You have a hot filament, and the photons are produced by atoms. They're released as a result of the energy in these atoms gets released in the form of photons. And so these photons are all streaming out from different places on this hot filament, and it's all kind of a random arrangement of photons, so-called incoherent light. Okay, photons have an interesting characteristic shared by some other kinds of particles, but that they're so-called bosons, and the particles like that have this feature that they like to always be in the same state as their neighbors. And they like to do that for reasons of quantum mechanics that we're starting to understand in our models of physics. But in ordinary quantum mechanics, it's just one of those things which it is a fact that bosons like to be in the same state. And that means by same state, it means they're going in the same direction, they have the same momentum. And if you, so here's how that actually happens. When you are thinking about photons bouncing around and they can interact with different things, they can go in different states and so on, the formulae that determine the way that happens, it's, well, I guess so-called transport equations that are determining sort of what's the probability that a particle will bounce with a certain momentum, will do things in a certain way. So there's an ordinary kind of way that you work that out, which just says it doesn't matter what the momentum is. Well, yeah, in a first approximate, it doesn't matter how many particles are already there. It doesn't matter what the density of particles is. It's just the amount of, each bounce is independent. Okay, there are some particles called fermions, which have the property that if there is a particle already in that state, you can't put another fermion into that state. Bosons have the opposite property. They have the property that in this formula that determines kind of the sort of the interactions between these things, there's an extra factor of square root of n, where n is the number of particles that are already in that state. And that extra factor means these particles like to all get together in the same state. And so what happens in a laser is that laser stands for light amplification by stimulated emission of radiation. I think I've run out of time to the point of, I'll explain that another time, how in detail that works. But basically, the idea is that in a laser, all the photons, not for the same reason as molecules in a solid are lined up, that has to do with mechanical forces between them. Instead, the photons in a laser are arranged to be in the same state, same frequency, which means same color of laser light, going in the same direction, a definite beam going in a definite direction. They're arranged by quantum mechanical processes to be in that same state. And that's kind of the analog of being in a solid phase for atoms in a material is in light. It's coherent light where all of the photons are kind of lined up in the same direction and with the same energy. So that would kind of be the analog of that. And there isn't an ordinary analog of temperature. You could probably define that. Let me think about that for a second. Yeah, actually you could define that. People don't usually do it. Usually people say that lasers are the result of negative temperatures for reasons I can explain another time. Negative temperatures in the material lead to lasers, et cetera, et cetera, et cetera. But when you think about a laser, you can think about a perfectly coherent beam of light where all the photons are exactly arranged in the same direction, same, et cetera. That's kind of like the zero temperature version. And you can think of it as when there are little deviations from that, there are photons that aren't quite, that are in slightly different states and aren't quite aligned in the same state. You could think about that a little bit as being like temperature, and people don't usually do that. And I'm not quite sure why. You certainly could think about it that way. I mean, I think usually one is thinking about it's just a laser and it's got this sort of precise alignment rather than how does it deviate from being a laser. And usually the deviations are measured in terms of the way the beam for the laser spreads and so on, which could probably be thought about in terms of some kind of temperature-like quantity. All right, I think we ran out of time here, but lots of lovely questions, and I can see many more for next week. I will probably not be in my usual location next week, and I'll try to do this at the same time next week. Might be from a different location. Maybe I'll even have a live audience next week. That'd be fun. That'd be different. In any case, I look forward to seeing you all, hopefully next week, if not the week after. And remember, there is a form where you can send in questions you'd like me to try and address. Yeah, I'm told I'm supposed to pitch other things I'm doing. Let's see, on Monday, I have the next episode in my walkthrough of my big book from 20 years ago, A New Kind of Science. And Monday, I'm doing kind of a walkthrough of the chapter called Two Dimensions and Beyond. Let's see. I think, as I mentioned at the beginning, there's now a bot that's saying what I'm going to be doing, which I don't even know. I don't know what it actually looks at. The bot is a bot. It's probably looking at my calendar or something. In any case, it will hopefully correctly, and I don't know whether the bot has a sense of humor and might say crazy things too, will be announcing other live streams and other things that I am doing. With that, I should probably disappear. So